So what did we do last time? So we kind of finished up the quaternion story, and hopefully you now have like all the kind of bits and pieces you need to do stuff with quaternions, and hopefully that like weird planar geometric story was somewhat enlightening, and now they make some more sense to you. And then we kind of talked a little bit about rigid bodies, mostly kind of definition stuff, and then we talked about inertia um, matrices. So, I mean, you can get kind of fancy and anal about the definitions of these things. Uh, so moment of inertia, inertia tensor, I don't know, inertia, at least like interchangeable. We're just going to call it inertia in here. And, you know what we're talking about. Um, and we won't be too pedantic about that. Okay, so that's kind of what we did last time. And then today, we're going to talk about rigid body dynamics, starting with Euler's equation, which I think most of you've seen before. And we're going to do a whole bunch of stuff with that, probably this time and next time. Hopefully today we'll get into talking about stability of kind of rotating objects. We're going to talk about energy dissipation and all that good stuff. Hopefully explaining the fun Explorer 1 anomaly that we talked about the other day and the whole flat spin thing. We'll see how far we get today. All right. Any questions about anything from last time, technically, or anything? Okay, cool. Let's do it. So first thing today, Euler's equation. And has anyone not seen this before? I think everyone's actually seen this before, right? Yeah, okay. So we're gonna kind of derive it, and then because we're gonna use some stuff with this. So the first thing to say is this is basically just a statement of conservation of angular momentum. So in an inertial frame, this is the angular momentum. And this thing, unless you have any torques on the thing, it's a constant, right? If you add torques, which we will be doing, that is, let's see, which one?
Sorry, the first line of the equation.
First, that's an H with a little n for Newtonian reference frame. Okay, so with torques, it looks just like F equals ma, right? So we're going to do this kind of thing. So it's literally just, H dot equals tau in the n frame. And then we're going to kind of, so if we were to take this and naively kind of diff it, like diff the expression above, you'd get, this term, which is reasonable, but then you're also going to get a J dot term because the inertia is not fixed in the rotating frame. And this is super messy and terrible, and we don't want to do this. So instead, the move is to write down these dynamics in the rotating frame where J is constant. That's way more convenient. So almost everything we do in here, we're always going to be dealing with stuff in the body frame. Just as a kind of recap from last time, as a brief aside, when we talked about kind of diffing things in rotating frames, kind of have this. So random vector x, we have this transformation from the body to inertial frame with the rotation matrix. And if I diff this with respect to time, I get, just from the kind of standard product rule, freshman calculus kind of stuff, we get this. And then now we have this nice little recipe. So essentially, the thing to remember is that anytime you see a q dot equals q times omega hat. That's basically what we got to when we talked about rotation matrix kinematics, right? So now you can just do this stuff, and everywhere you see a q dot, you just plug that in. So now we've got this. And now we kind of, rewrite that slightly as you can pull the q out, and this is x dot in the body frame plus omega cross x, again, all in the body frame. Okay, so that's what we got last time. So this will come up a lot. And so if we just kind of use that result on the momentum, we've got h dot in the n frame is torque in the n frame. And then if we rewrite that in the body frame using that little result from above, we get h dot in the body frame plus omega cross H, right? All in the body frame now. And if I take this and left multiply everything by Q transpose, that's going to get rid of this Q, and then it's going to put that torque now in the body frame. And so now we can rewrite the entire thing in the body frame, which is what we're after. So this is what you get now. And now all we're going to do is plug in H in the body frame is J omega, just a definition of angular momentum. And that's going to give us, I guess we'll keep the superscripts for now because we've got multiple frames floating around, but we're going to drop them after this because everything's always going to be in the body frame. Okay, so this is it. That's what we were after. This is Euler's equation for I guess, forced rigid body, right? Okay, so yeah, like I said, we're going to start dropping the superscripts with the frames because this is always going to be in the body frame. I'll only use superscripts when it's ambiguous or when we're doing stuff in multiple frames and going back and forth. And then one little kind of nugget from here that's extremely common is, so last time we talked about inertia matrices, inertia tensors, whatever. We talked about this idea of principal axes, right? Which are the coordinates in which the inertia matrix becomes diagonal, right? And that's essentially the symmetry axes of the body, right? So if I do that on this equation and rotate the frame such that J is diagonal, this thing can simplify down into three scalar equations, three coupled scalar equations. So we'll write those down real quick. They show up. They're useful for analysis and stuff, which we will use them. So in principal axes, this reduces down to the following thing. And I guess these all have little p superscripts for principal axes if you want to be really pedantic about it. And this is really easy to derive, right? You just plug in a diagonal J up there and write it out in components. It's basically just kind of expanding that cross product out to get this middle term. Okay, so these things, this set of three equations is usually referred to as Euler's equations with an S. And let's see, who's seen these before? Everybody more or less seen these before? Yeah. These are useful more for doing kind of analytic things. That one's the one you actually want in practice for simulation and stuff. This is the general case. And then one extra note about this is when we talk about principal axes and we kind of number the axes 1, 2, 3 like this by convention, which I think is more or less standard in the aerospace world, we assume that these are ordered such that J11 is the smallest one, J22 is the intermediate one, and J33 is the biggest one. And we call those the minor axis, intermediate axis, and major axis of the body, or of the inertia. So far, so good. Questions? Yeah.
Slight question. Can you scroll up just a little bit?
Yeah.
All right, you see this constant equation?
Yeah.
So it looks like H dot is like the same as J.
Oh, sorry. This should have a dot on it. Yeah. Right. So in the body frame, J is constant. So when you take H equals J omega and you diff it to get H dot, there's just no j dot 0, so you just get the j omega dot term. That's basically what's going on there. Yeah, sorry, that's just my bad on the writings. Okay, everybody good so far? Okay, here's next question. Okay, so we got some ODEs here. Everyone know what the idea of an equilibrium point of a dynamical system is? Can anyone give me a quick definition of equilibrium point? I believe you. Yeah, somebody just.
When uh the force is important 0.
Yeah, basically, if you've got a state X, it's when X dot's 0. It's when the thing will park in a given configuration and not move, basically, right? So yeah, for a generic system, it means, like X dot equals 0. In our case, what we're talking about here is when omega dot is 0. So it means that the thing is spinning. Basically, it's a clean spin about a constant axis where it's not wobbling, mutating, et cetera, where it's just kind of hanging out at a constant spin. So question now is, how many equilibria does a spinning body have? Anyone have any thoughts on this? I'll let you think about it for a sec. Yeah, what you got? Two? Nope. Why two?
I don't know. It's something I was remembering from a video I saw a long time ago.
Okay. All right. So there's a few ways to think about this. I'm going to show you something that's maybe slightly useful in general. So here's Euler's equation that we just found out in the unforced case, right? So this is with no external torques. You get this situation. Oh yeah, so what I'm going to do is rewrite this. So right now we have it all kind of written in terms of omega, which is what we'll usually be using, but we can actually rewrite this in terms of h, which is sort of equally valid. So that first term is h dot, and then the next term, I can write omega as j inverse h, and obviously j omega is just h, right? So I can write it this way, and then I can sort of slightly rearrange this and write it as h dot equals h cross j inverse h. So it's kind of the same idea, just rewritten slightly, and this maybe is somewhat illuminating. We're going to do some stuff with this later. Okay, so equilibrium here means h dot is 0, means that this h cross j inverse h equals 0. Okay, so when is that true? When is this cross product expression going to equal 0? Basically, when's a cross product equal 0 in general? Anybody? Help me out. Yeah. Yeah, so when the vectors are parallel, right? Okay, so when are the vectors, when is h and j inverse h going to be parallel? So in general, if I have a matrix and I say that like ax is parallel to x, what does that mean? You've definitely seen this before. I'll make it even easier. So parallel means ax equals lambda x, right? For some scalar lambda. What's that scalar called? Yeah, so when is a vector, so if I plug an x into, like if I multiply it by a matrix and I get out a vector that's parallel to the one I plugged in, that means that vector is an eigenvector of the matrix, right? So it just comes back as a parallel equals scaled copy of the original, right? Okay, cool. So then for these guys to be parallel, what's got to be true about h? Exactly, yeah. Which is the same as actually an eigenvector of j, right? Okay, is everyone cool with that? That's what's going on, right? So For this to work out, then we've got H is an eigenvector of the inertia, which is also equivalent to saying that H is parallel to one of the principal axes of the inertia matrix, right? Okay, so then we're saying it's like 3 or 6, depending on how you want to count. Depending on, if you count the negative sign, as a separate thing or not. I think we'll call it 6. And these are going to be in the plus or minus these principal axes directions. You can also see that, by the way, from these guys. So basically, if I get rid of this and I say, that's got to be 0, basically it means that like these guys have to be 0, right? That you can't have any component along omega 1, omega 2, which kind of translates into sort of clean spin about just the principal axis, right? But I think the eigenvector version is a little bit more insightful. Okay, so any questions about this? Yeah.
Doesn't that go against like the Hemispheric theorem?
Absolutely not. We're going to do that right now. Yeah. So that's a different thing. That's a stability thing, which is literally what we're going to do next. After I show it to you.
But
And
it's not equilibrium.
it is. So equilibria can be stable or unstable, right?
Oh,
So the way we're talking about here, so stable equilibrium is like pendulum like this, right? Unstable equilibrium is pendulum up, right? So that's an equilibrium. Like in theory, if you could perfectly balance it up there, that is an equilibrium point, but it's unstable. For tiny, tiny perturbation, if I blow on it, it's going to go, it's going to go off and blow up on you, right? So that's what's going on. So we're going to talk about that next. And before we get to talking about it, I'm going to show it to you. Ah, okay. Yeah. So this is a subtle thing. We will talk about this. I gotta go away. What is happening? Okay, things have not blown up entirely. We're okay. Gotta share the screen. Okay, so here's my fun animations that I spent too much time on that I will share with all of you. Okay, so this is, so here's all our quaternion stuff from last time. Here's our dynamics. So this is Euler's equation. So here's the quaternion kinematics that we had last time. And now we've actually got Euler. So this is the free rigid body dynamics, right, that we just wrote down. Cool. That's it. Those are the dynamics. And we're going to do Runge-Kutta like we talked about last time. And we're going to do a little renormalize the quaternion trick inside there. So things stay sane. We're going to make up for our, a very simple, so this is a box with, inertias 1, 2, 3. Pretty simple. And then we're going to simulate this thing for, I don't know, a minute and a half or so. And we're going to do some initial conditions here. Let's start, we'll do random initial conditions first, just to kind of like see what that looks like. We're going to simulate it. And then we can visualize it. Cool. Okay, so this should just kind of tumble. Random initial conditions. Yeah, it's kind of tumbling around. You get the idea. All right, so let's go try. So let's give it initial conditions that are along these principal axes and take a look. So this, right, we made the inertia diagonal here. So this is easy. So I can spin this about the 3 principal axes, and I'm going to just kind of to make it slightly more interesting, I'm going to add little noise perturbation. So first we'll start with so this is the first axis. So this is the smallest inertia. So that's the skinny axis. This is hot dog style, right? So let's do that. Okay, so hot dog, that's kind of a big, I think my rand n gave me a pretty big perturbation there, but you can see kind of what's happening. So it's spinning with the hot dog axis, and then it's wobbling around that axis, right? So that wobble is called nutation, and we're going to talk about where that comes from in a sec. But it's still more or less staying around that hot dog spin just with a little wobble, right? And we can try the same thing. So now we'll do the pancake spin, the fat axis. Same story, little perturbation. And you will see, hopefully. Okay, there's hot dogs, or this is the hamburger style, and it's got, you can see now, random gave me a tinier random perturbation this time, but you can see it's wobbling a little bit, but it's kind of staying around the hamburger situation. And now the fun one that everyone's already knows about, we're going to do the intermediate one, right? So this is the so-called tennis racket effect. And we'll see what happens now. So it starts spinning and then it flips. Now it spins kind of the other way, a couple times, flips. And sort of depending on how big that perturbation is, you can get a handful of spins before it flips. So if I turn this down and make it kind of, so I guess maybe we'll try a couple things. So I'll set this to 0. And so in a computer, if everything's exactly right, exactly 0, it will spin about that axis. So let's see. So there we can make it spin about that axis if I have no noise and everything's exactly perfect. But this is equivalent to like balancing a pendulum upside down, right? So it's basically never going to happen in real life. And if I add even the tiniest perturbation here, so if I add like, I don't know, like 1e minus 3 kind of stuff, you will see that it will start out, doing that, but then it is unstable. So after a short amount of time, that perturbation will grow. It's kind of going to blow up, and then it's going to flip around. And this has this super interesting behavior where this is a pretty small perturbation. So it's going to kind of hang out around the intermediate axis a bit longer, but it basically is always going to end up blowing up. And then in this case, for reasons that'll become clear maybe in 10 minutes or so, you get this effect where it flips around, spins, flips around, spins a little bit. It's super interesting to watch. There's some good ISS videos of an astronaut spinning a T-wrench and getting this, which I should have pulled up. They're on YouTube. Maybe I'll do that at the end of class. Okay, cool. That's fun and weird. Thoughts, questions? Anyone want to try anything else? Okay, back to the math. So now the question is obviously like, why does that happen? What's going on there? Okay, so let's go back to iPad. Hey, it's working. Okay, cool. So we got that. And basically the initial kind of poking around outcome here is yeah, spin about that intermediate axis. You get this kind of flip behavior, right? Okay, so let's try to figure out why that's happening and dig in a little bit deeper. So what we're gonna kind of look at now is which of these is stable. And we already kind of know the answer from the simulation. And now we're gonna kind of try to explain why. So who's done kind of like basic stability analysis before and thought about like checking stability of dynamics? Has anyone not done this before? Okay. Can't remember, maybe kind of. Okay. So we'll take it a little slow. And then like if you guys have questions, definitely reach out. There is a 5-minute linear stability analysis kind of discussion we could have. Since it's 3 of you guys, come bug me after class and I'll show you that. The basic idea is for any nonlinear system about locally in the neighborhood of an equilibrium, you can linearize the dynamics and then look at the linear system. So that's what we're going to do first. We're going to linearize about each principal axis. And we're going to assume, like before, like we said, that these are ordered such that, number 1's the smallest, 2's in the middle, and 3's the biggest one by convention. All right, so first thing we're going to do is look at kind of spin about the small skinny axis. So we're going to say that's spinning with some omega naught, and that's much bigger than the other components of omega. So omega 2, omega 3 are tiny, right? So we're going to have some nominal spin about omega 1, and then we're going to linearize the equations for omega 2 and omega 3, and like assume that those components are small, blah, 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 throw out second order and higher terms, right? So if we do that, so what I'm doing to be clear is we're going to look at these equations. So in the omega 1 case, we're assuming omega 2, omega 3 are small. So this is a second order term, goes away. So I'm going to drop that. So this whole equation basically drops out and does nothing. The other two equations, when I look at this term, this is going to be like our nominal big omega. And then so in terms of this one, this will be a constant, and then this will get a linear term from this guy. Similarly here, this is constant. We're going to get a linear term for this guy. So we're going to end up with two coupled equations for the omega 2 and omega 3 components. And this one basically to first order is constant and kind of drops out. Make sense? That's like how we're going to linearize it. So I'm just going to like write that down. It's not hard to do this. That's kind of the recipe. So we're going to get an equation for omega 2 here that looks like this. And then an equation for omega 3 that looks like this. Okay. So this now, if you've done, any kind of linear systems stuff, this is a pair of coupled linear first order ODEs. So we can write these down as a little matrix equation. And just to kind of save on notation and not go nuts, we're going to call this guy the coefficient on omega 3 here. So this is all constants, right? Omega naught's a constant. These are the inertias constant. So this constant we're going to call alpha 1. And then this constant over here, we're going to call alpha 2. And we can now stack those equations. And most of you, I think, have seen this before, but we'll go a little slow. And then for those who haven't seen this kind of thing, come talk to me after class and I'll show you what's going on. So omega 2, omega 3, we're going to stack. And so we've got, this is, omega 2 dot, omega 3 dot. And we can write those two equations as a little matrix equation. So this is alpha 1 times omega 3, then alpha 2 times omega 2, right? So it's a little 2 by 2 matrix equation. And if you've done linear systems before, this looks like x dot equals a times x. Right. Okay. So those who have done linear system stuff before, how do I check if this linear system is stable? Got one person who likes to speak up. Anyone else? Yeah.
Yeah.
So you can do that. That's a lot more complicated, and that's the nonlinear stuff, which is overkill here because we're dealing with a linear system. We will kind of touch on that later. We're actually going to do some Lyapunov stuff, but I'm not going to call it that because we don't need to here, and I didn't want to go there. But it's cool that you know about that. For a linear system, anyone have any thoughts? How do I know if this thing's going to blow up or not?
Yeah, I think values are stable.
That's right. Yeah. So if this thing has negative eigenvalues, it means things are decaying, right? The real parts are negative, right? And if it has positive real part, that means this thing's going to blow up exponentially, right? So the way to think about that, right, is remember the solution of this is e to the AT. So e to the positive number blows up, e to the negative number decays. That's it, right? So we're going to check the eigenvalues. Positive, bad, blow up. Negative, good, decay. So let's do that real quick. So it turns out for 2 by 2 matrices, checking eigenvalues is really easy. And there's like a closed form. And I will just tell it to you right now. You can also just plug this into MATLAB or whatever. So for 2 by 2, there's a little quadratic equation you can solve that looks like this. That's the trace, and that's the determinant. So if I just kind of stare at that real quick, what's the trace of this matrix? 0. 0 is on the diagonal. So it literally ends up just being lambda squared equals minus determinant of A. And the determinant is, 0 minus alpha 1, alpha 2, right? So we get then lambda equals plus minus square root alpha 1, alpha 2. Okay. What signs do alpha 1 and alpha 2 have here? You want to tell me? What sign is alpha 1? Why? Is bigger. Cool. Okay, so alpha 1's positive. How about alpha 2? Negative. Same reason, right? Like the 1, 1 is smaller than 2, 2. Cool. Okay, so we got one positive, one negative. So now, what's this guy looking like? It's a negative inside the square root. So this is imaginary. So this is a pair of pure imaginary eigenvalues. What does that tell us? I know a bunch of you guys know this. Yeah, come on.
Just gonna oscillate.
Yeah, so this looks like now a simple harmonic oscillator, right? Okay, so there's a couple things to say about this. So number one, just to be perfectly clear and like rigorous about this, if you're really doing this in real life and you find you have a linearization that gives you pure imaginary eigenvalues, that corresponds to some kind of oscillatory behavior, but you cannot make stability determinations if the eigenvalues come out pure imaginary. This basically means that the next higher order term in the Taylor series is going to matter. And so we'll talk about this next, but basically you can't really make conclusions, but for here, qualitatively, this kind of corresponds to simple harmonic oscillator stuff. And empirically from the videos, when I added little perturbations, what happened? It kind of wobbled around, right? Around that nominal spin axis. So what's happening here is basically, if you're spinning out a principal axis with small perturbations, it looks like a simple harmonic oscillator in the other two axes. So it's going to spin and then it's going to wobble a tiny bit around that spin axis when you perturb it. Okay, so this is marginally stable, is the lingo. And actually, in this kind of situation, if you're really trying to be rigorous about stability analysis, you have to go do some Lyapunov stuff because this doesn't really tell you. But that's good enough for us. This is oscillatory. And so that's kind of what's going on. And then the oscillatory motion of a spinning rigid body in this context, does anyone know what it's called? So when a rigid body is spinning and it does the little wobble thing like this, it's called nutation. Ever heard of that before? Okay, so physicists mean sometimes weird different things when they say nutation, and they have all kinds of weird crap in terms of Euler angles. Remember, Euler angles are bad for you. You can go tell your physics major friends that they're doing bad things. And this is what nutation means. They have some weird definition in terms of Euler angle derivatives. That's complete garbage, nonsense. Don't pay attention to the physicists. Okay, so this is called nutation. Cool. And let's see. And by the way, for a given rigid body, and given its inertia, and given this kind of omega naught, like the nominal spin, you can calculate the nutation frequency, right? So what's the nutation frequency here? For those who know what's up in terms of linear systems, it's basically those eigenvalues, right? Those are giving you it's like a j omega kind of situation. So those eigenvalues tell you the frequency of oscillation. She can back that out. That's on the homework, by the way. So go look into that a little bit. And what else? Yeah, there's a few other things you can do. But yeah, I think that's what we need from this. So that's what's going on. Next up, and the fun one, is we're going to look at the omega 2 situation. So this was that intermediate one that did some crazy stuff, right? So here we're going to do omega 2 is kind of this omega naught, and then these guys are tiny. The other omega 1, omega 3 components are tiny. So it's the same exact thing. We're going to get these two components, the perpendicular components are going to look like little simple harmonic oscillator type things. I'm just going to write those out real quick. Something like 3, and then we're going to do the same thing, alpha 1, alpha 2. And kind of plug these in and check our eigenvalues. So here again, plus minus square root alpha 1, alpha 2. Okay, so now let's look at the signs again. What's alpha 1? These are way too quiet. So the third one's biggest. That one's negative. How about this one? Also negative. This 2 is bigger than 1. Okay, so they're both negative. So now this is positive inside the square root. It's real. So we get a real pair. We get a positive and a negative eigenvalue. What does that mean in stability terms? Bad news, right? So it's okay. Like basically the story is, one of them is stable, one of them unstable. It doesn't matter. If I have any kind of component along the unstable direction, it's e to the positive number over time. It's going to blow up, right? Okay, so we have so if you have any positive eigenvalues, it's bad news. So this is unstable. And that is kind of what was going on in the blow-up situation we saw before. And we'll get into a little bit more kind of explaining that oscillatory motion. But the bottom line is that intermediate axis of inertia is never stable. And you don't want to spin a spacecraft about the intermediate axis, and it will kind of blow up and do bad, flippy, tumbly things on you in general. Okay, and then the last one, which we kind of already know what the answer is going to be from the simulation. The major axis, we can kind of repeat the analysis and there will not be any surprises. So here we get oscillating things about the first and second axes. And let's see. Alpha 1, alpha 2. And then here we got, similar to before, 1 negative, 1 positive. So that's going to give us maybe I'll write this in here. These were both negative. Oops. So this guy is pure imaginary. And once again, kind of this marginally stable oscillatory situation like the minor axis. So the takeaway from this kind of whole linear stability story is that, and we'll caveat this. So in the absence of any kind of,
Be like not much greater than the other one.
Yeah.
It was like in the sim you were using 0.1, right? As the like,
you can make it arbitrarily small.
well, like what would be the upper?
What's the upper? Yeah. Well, I think we'll kind of get to this. There isn't really one. Like you're going to get oscillatory motion about those other two, about the major and minor, and then the intermediate one's always unstable. In terms of like caveating that and how big is small and everything, the linear analysis doesn't really tell you this. You have to kind of think about some nonlinear things to get there, and we're going to do that next, actually. And it is technically like sort of a Lyapunov analysis, though we're not going to kind of bring out the formal Lyapunov machinery in here because we don't really need it. Okay, so in the absence of any kind of like energy dissipation, other perturbations, flexible modes, et cetera, which is a kind of a big caveat. The major and minor axes are marginally stable, we'll say stable, while the intermediate axis is unstable. Okay, so now worth a box. What should we talk about next? Okay, so so far we have like a numerical way of getting at this stuff, right? We have an ODE. Now we're going to try to do, which is going to help a whole bunch when we try to do kind of talk about so we still haven't explained the Explorer 1 thing, the flat spin thing, right? So far we know, yeah, intermediate axis bad. Explorer 1 was a hot dog spinner and it kind of tumbled and went out of control, right? So why? So we're trying to work up to that, and to kind of get there and get you some more intuition, what we're going to do now is talk about solutions of Euler's equation, kind of the space of solutions, and we're going to show you this thing called the momentum sphere that helps kind of visualize this stuff and get some intuition. Okay, so one fun fact is, so Euler's equation, this is like a set of nonlinear coupled, ODEs. Usually there's no hope in solving nonlinear ODEs. Like just give up, use a computer. It turns out there are these like tiny little, needles in the haystack once in a while where you can exactly analytically solve a nonlinear differential equation. And this is actually one of them. Has anyone heard of Jacobi elliptic functions? It's kind of weird and arcane. So it turns out Euler's equation, these three equations, they do have a closed form analytic solution in terms of these things called Jacobi elliptic functions. Kind of funky. Turns out also, similarly, the nonlinear pendulum also does have an analytic solution, also in terms of these Jacobi elliptic functions. The only people who know about this are like weird, arcane, like 19th century kind of people who are fans of like 1800s vintage, mathematical physics. They're kind of a footnote of history. You should know that is a thing, but caveat, it only applies to like the exact kind of unforced, case. And it's actually not that useful in practice. It's kind of ugly. So just so you know, I feel like you should know about this. There is an analytic solution. And, now you know, if it ever comes up, you can go look it up. But it's ugly and not that useful in my opinion. I would say, the main reason it's not very useful in an engineering sense is that as soon as you add any kind of perturbation or add control torques or anything else, it breaks the analytic solution. So you got to go use numerical integration anyway. So we're not going to bother with it. Usually we'll use like a Runge-Kutta method on a computer. And this is kind of like the set of ideas we're kind of dealing with now are what would be called dynamical systems theory. So there's a lot of insight you can gain by looking at kind of geometric, kind of qualitative behavior of the solutions, without actually needing to solve the equations analytically. So that's what we're going to kind of look at now. And you can make pretty pictures. Okay, so we're going to revisit the version of Euler's equation that we wrote out in terms of momentum instead of omega. So we have in general that angular momentum is conserved, right? So this means that no matter what happens, if I have a free rigid body, no applied torques, it's just tumbling around. Because of this conservation law, the solutions have to lie on a sphere always, right? So if momentum is conserved, if I write the dynamics in terms of H, that H vector is confined to the surface of a sphere, right? So we're going to call that the momentum sphere. And there's one other conserved quantity that we talked about, right? What's that? Kinetic energy. And in terms of H, so we wrote that out before, like so. Omega, well, I've got a 1/2 in there by convention, though it really doesn't matter. So we got 1/2 omega transpose J omega. I can rewrite that in terms of H as H transpose J inverse H, right? And that's conserved. So what kind of surface does that describe? Anyone tell me? Well, quadratic form with like so if I have this kind of thing is a constant. How about if J is the identity, what is it? If J is identity, it's just H transpose, it's H squared equals constant, right? It's the same as the other one. That would be a sphere, right? Okay, what if H is a positive, or J is a positive definite matrix? That basically means you're stretching the sphere along a couple of different directions into an ellipsoid. So this thing now, so angular momentum, sphere, energy conservation is an ellipsoid, like an egg, right? So this is the energy ellipsoid. Cool. Okay, so now we've got these two conserved things, and we know the solutions have to lie on this momentum sphere and this energy ellipsoid. So if I put that together, this that's just what we were using before for kinetic energy.
Oh, right.
Yeah, no biggie. Okay, so now if both of these things have to be true, I know that the solutions, like the trajectories of the system, live on the intersection of these two shapes, right? So they got to satisfy both things. So now if I plot both of those, the possible trajectories the system can live on are the intersections of these two shapes. That defines the trajectory, right? So this doesn't tell you, and we didn't solve any ODEs here, right? So that's kind of cool. So I don't know the time evolution, but I know the shape of the trajectory in space, which is kind of cool, right? So this is kind of qualitative behavior I can figure out without actually having to solve the equation. Just with a little geometry. Okay, so trajectories are intersections of these shapes. And you can kind of like visualize this. I'll have okay, so if I'm thinking about the equilibria, so I've got like, minor axis, major axis kind of stuff. One of those will look like this, where they're just touching at a point, right? So this might be like the minimum energy. This is actually the major axis one, where they just touch at 2 points. So that's equilibrium, right? And you've got two options. And then the other case, which be like the maximum energy situation, is where it looks like this, and they're just touching at these other 2 points. And this would be the maximum energy case. And that's minor axis, where these are going to intersect at points. In general, if it's somewhere in between, they're going to intersect at some weird, complicated curve that in general looks kind of like a Pringles, edge of a Pringles chip or something. Okay, cool.
Just on the first illustration.
So yeah, I'm bad at drawing. I'm going to show you in code with pretty pictures now. I can't draw. So I anticipated that issue. All right, so let's get the code up again. All right, so we had this whole thing. Let's go back and run this again. And let's pick some nice initial conditions. Let's pick, we'll do the minor axis again. Maybe I'll add a little bit more perturbation here so it's clearly visible. So we're going to do the same thing again. We already saw this movie. And now what I'm going to do is, so yeah, cool. We've seen that. I'm going to calculate the momentum and the energy. I guess we'll plot these for fun. I should have done this before, probably. Hopefully this doesn't die on me now for no reason. Okay, cool. So energy should be conserved, and this is like 1e minus 7. So this is like pretty well conserved. That's just numerical error. And then momentum should be conserved in the inertial frame, and that looks pretty good, right? All three components are constant. So now we're going to draw this momentum sphere thing. Go ahead and screw anything up. And hopefully I didn't break anything. Okay, let's try this. Thinking about it. Okay, cool. So we have momentum sphere. Green dots are the stable equilibria, so the minor and the major. Red dots are the unstable ones, the intermediate ones. And I just kicked off with, x component equals 1 with a little perturbation. And this is our nice little stable oscillatory behavior, right? So that's a nice little periodic orbit around the equilibrium. That kind of all makes sense, right? So that's what the trajectory looks like. Let me give it a bigger nudge, a bigger perturbation. We'll try that one more time and just kind of plot some more trajectories. So I'll go make this say 0.5, and hopefully that doesn't do anything too insane. That looks like it's being really slow. I'll try to plot that. Hopefully this doesn't. Meshcat is not happy right now. The animation thing is hanging, which is annoying. All right, we're gonna kill that, maybe. Okay. It must die. All right, let's try again. I won't run the animations this time. Okay, that's good. Let's go down here, do the plots. Why? Why do you do this to me? Everything worked so well last night. Yep. Okay, let's see. Okay, so yeah, slightly bigger. And you can kind of see now it's a little bigger. It starts to look a little bit more Pringle shaped. Get the idea. So let's go do a couple more. I think if this takes forever, it might get a little challenging. I might punt and try to throw a picture in. Let's try now the major axis. And we will make a couple up there. I'll get you the idea.
In your plot, you're showing the momentum sphere.
Yes.
You're not rendering the full ellipsoid. You're just rendering.
I'm not drawing the ellipsoid at all.
Okay.
I'm rendering the trajectories, which are those intersections, to be clear. Right? So but I haven't drawn the ellipsoid. Okay, so right now what we did is so this is the minor axis, this is the major axis with a little perturbation, and this is kind of that oscillatory motion that we're familiar with. So oscillations correspond to like closed periodic orbits. So these look reasonable. And in general, they kind of look like Pringle shapes, right? You kind of get that. Okay, so we could run a few more of these. Because it's being slow, I probably won't do too many more. Let me run an intermediate one, and you'll sort of start to see now what those look like and kind of geometrically what's going on. I'm going to turn the perturbation down on here so it looks a little cooler. Let's try that. So that goes. So that's fine. The plotting code's kind of sucking. Okay, so, oh yeah, I wanted to change the color on that too. To differentiate. Hopefully this is not terrible. It's kind of, okay, cool. So what's going on here is, so we started out in the neighborhood of, say, this guy with a little perturbation, and what's happening is it's blowing up. It's going all the way over here to the other unstable equilibrium. And then it's hanging out there for a little bit, and then it's kind of going back, flipping again, back to here. So everyone see what's going on there geometrically? So that's what that flipping behavior looks like on this momentum sphere. And if I run a handful more of these, which given that this is being kind of slow, it's maybe going to be kind of annoying. What this is actually going to do, which is kind of cool, and if we had time, I would plot a whole bunch more of these. That one wasn't interesting. It looks basically the same. It is a random perturbation, so we're roll the dice a few times to get this to look cool. But basically what's going to happen is, let's see if maybe I'll give this 1 or 2 more tries. Yeah, okay, that's good. Perfect. So check this out. So we have one of those unstable trajectories kind of goes here. The other one kind of goes here, and it splits the momentum sphere into 4 regions around the stable equilibrium, right? So here's the stable ones. So in here, we got the stable equilibrium, and we have these oscillatory motions kind of in this. This is called a basin of attraction, right? So we have oscillating about the minor and the major axes here, and that's kind of true in all these 4 zones. And then the unstable trajectories that correspond to that flipping motion, they partition the stable regions around each of the stable equilibrium points. Those guys are sometimes called separatrices. One's called a separatrix. The other fancy math name for these things is a heteroclinic connection. So a heteroclinic connection is fancy dynamical systems speak for a trajectory that connects 2 equilibrium points. Kind of fun. So hopefully that gives you some idea of what's going on. Like the unstable ones, you get this flipping motion that corresponds to like flipping back and forth between these 2 antipodal points on this momentum sphere. And those trajectories are actually the dividing lines between the stable basins. And a thing that actually shows up quite a bit with spinning spacecraft is something called flat spin recovery. So we talked about how, explore 1, flat spin, bad. So what that corresponds to is you're ending up here, right? From here. So one of the kind of interesting nuggets there is to sort of get yourself out of a flat spin, you end up having to traverse across the separatrix. And that's tricky business. And it's hard actually to do that. You kind of end up pumping energy in and spiraling out. And then you're going to end up on one of these guys. And the issue is it's hard to control which of these basins you end up in, because you have to kind of cross one of these unstable points. And so it's kind of fun. It's a fun control problem. I've done a bunch of weird stuff with that. Okay, that mostly worked. Any thoughts, questions? Anyone want to try anything? So you can flesh this out some more. You can plot a bunch more trajectories. But basically, you get little Pringle loops, and then you get this like kind of separating behavior. Okay, done. Yeah.
What are the axes here?
So this is momentum sphere. The ones that are plotted, the little dots are the eigenvectors of the inertia, right?
I assume the axes of this graphic.
I see. I've normalized everything. This is just I normalized the norm of the momentum to 1 for plotting purposes.
Okay.
The units here would be angular momentum.
Okay.
So I'm plotting the angular momentum vectors, right? And sort of trying to show you they live on a sphere of norm, however big your angular momentum is. There's 6 equilibria. They're split into these regions, blah, blah, blah. Cool. Any other questions, thoughts about this? I don't know. I think this is cool. Okay. Moving on then. Back to the iPad. Okay, so now you've seen sort of all right. Now we got some time, so see how far we get on this next bit. Okay, so now you got this momentum sphere picture. We talked about the linear stability thing, you understand the basins, minor, major, intermediate. The next thing to talk about, which is going to explain the Explorer 1 situation, is energy dissipation. I think I'll just start a new page for this. Okay, so the first thing to talk about, which we kind of already maybe alluded to a little bit, is if I give you a constant angular momentum, you have that momentum sphere picture. We have talked about the energy thing. There are sort of maximum and minimum energy states for a given angular momentum. And so this is pretty clear if I write out kind of just from the definition of kinetic energy. I have this, right? And now if I think about kinetic energy, omega transpose J omega, which we can write in terms of momentum as H J inverse H. Okay, so if this is unit length, constant, let's say norm one, whatever, how if I try to maximize the energy, what would I do? So I can choose the direction of H, right? It's the norm's constant. Let's say it's one. What direction is going to give me the maximum kinetic energy out of this thing? Think about eigenvalues and stuff again. Pretty straightforward. Linear algebra chops here. Thoughts? Yeah, I don't know.
Oh,
What you got?
the direction of the eigenvector that corresponds to the biggest.
Yeah, that's right. And it's the biggest eigenvalue of J inverse, which is the smallest eigenvalue of J. Right? Follow? So that means the minor axis of inertia, the skinny axis, is the one that has the most kinetic energy. And you can kind of hand wavy get at this intuitively by basically it's going to spin the fastest about the minor axis, right? Minor axis has the least inertia. So if we're given angular momentum, you're going to spin the fastest about the minor axis and the slowest about the major axis. And energy goes like omega squared. So spinning faster and slower has a big impact on this guy because it's squared. So if we kind of just to write that out, we're going to end up with maximum energy is going to look like this. It's 1 over the minor axis times norm h squared. That's just me writing this guy out, right? And then the minimum one is going to be where I've got, the big inertia in here times norm h squared. And so this corresponds to minor axis, major axis. Okay, so now we know the hot dog spin, the minor axis spin, that is a maximum energy state for this spinning body given a fixed angular momentum. So if there's any internal energy dissipation, which there always is from fluid slosh, flexible mode, weirdness, damping, etc., what's going to happen? How about Mr. Lyapunov? Want to tell me what's going to happen? By the way, this is a Lyapunov function, right? We're just talking to energy here. And it turns out this is a valid Lyapunov function for this system, and you can prove global Lyapunov stability using the energy argument in here. So we're basically doing the Lyapunov thing. I'm just not calling it that. But anyway, okay, so what's the deal with Lyapunov stability here? So if I tell you the energy is a Lyapunov function, what happens to prove that something's stable with the Lyapunov function?
It stays within. It doesn't go off to infinity.
Yeah. So the deal is you have your dynamics, you have your V. It's like a bowl, and then you want to prove that V dot is negative. It means you're always going downhill on the bowl. Okay. So here, V is the energy. You have energy dissipation that's sucking energy out of the system. So V dot's negative. Where's it going to land if I suck energy out? The bottom of the bowl, which is the minimum energy, which is what?
Oh, spinning about the major axis.
Hey, all right. Thanks, man. Okay, so yeah, so what we're saying here is that the major axis, which is the maximum energy, which is like a peak, that is unstable when you have energy dissipation because you're going to go downhill because we're sucking energy out with the energy dissipation. So if you have any energy dissipation, which you always do in practice from something, even if it's small, there's always some there, then only the major axis is really stable. It's the global energy minimum. It's at the bottom of the bowl, right? Okay. Does that make sense to everybody? All right. Thank you. Thank you. Hopefully I'm not like scaring you guys. I'm not trying to. I hate like talking at you for an hour and a half. It feels like I'm just speaking into the void. So I appreciate you when you actually, speak up. Okay. So only the major axis is stable. Since it is the minimum energy state. Boom. Box. Okay, so now I guess we should talk a little bit. I think we kind of talked about this last time, just touched on it briefly. So question is, where does energy dissipation come from? Thoughts? Yeah. That's a big one. Propellant tanks, etc. Flexible stuff. That's the Explorer 1 story. So damping from flexible structural things. There's one other one that's weird that I have personally seen happen that freaks me out. So maybe story time since we're running out of time. We flew a bunch of CubeSats last year called Pi 4. These were little tiny, like solid, there's no fluids, there's no flexy things really. They're little bricks. And we used a controller to spin them up and point the solar panels at the sun. So they're in a major axis spin pointing at the sun. They came out of the, I should say first, they came out, deployed tumbling, and they ended up in a flat spin, and then they ended up spinning down over time. Like their spin rates decreased over time. How the hell does that happen in space? There's no drag, there's nothing. Where's the angular momentum going? That means there's an external torque on the satellite, like spinning it down. Like, where is that coming from? That is weird.
Like radiation pressure.
No, not that. So, reasonable. I don't know. This is super weird. So it turns out there are also kind of weird electromagnetic effects. So in particular, this phenomenon called magnetic eddy current damping that comes from, magnet metal interactions. We're pretty sure this is what's going on. Some weird magnetic field interaction, but this is weird, and still I haven't fully gone down the rabbit hole to explain this. But there are electromagnetic effects that can do weird things too. Let's see, got like 5 minutes left. Let's see how far we can do. Okay, so I guess this is the story we have so far with this kind of damping effect, kind of energy dissipation. This is the story of Explorer 1, which I kind of hinted at the first day. This was the first US satellite. It was pointy and skinny, and it had a set of whip antennas that look like this, and it was deployed in a minor axis spin, spinning hot dog style. And very quickly after it was deployed, it started tumbling and then settled into a flat spin, and no one could explain why at the time. And this prompted like a rethinking of classical rigid body mechanics, and this kind of energy dissipation thing came about. And this is when people figured this out, basically in the late 50s from this first satellite. This was actually just like a couple months after Sputnik in 1958. Yeah, it was designed as a minor axis spinner. And ended up in a flat spin. Due to damping in the flexible antennas. Okay, that's like 4 minutes. I think the next one is it will take longer than 4 minutes, but because I spent too much time making animations, I want to show you the cool animation, make you want to come back for the math. So I'll tease the animation, and then we'll do the math next time. All right, so this is simulation with some energy dissipation, and we'll talk about the model of the energy dissipation next time. And this is a roughly Explorer 1 looking satellite. Actually, this is too stretched out. That violates the triangle inequality. We'll go with that. That's a long, skinny satellite with some damping, and I'll talk about the model next time. And we're going to start it out spinning about the major axis, the minor axis, hot dog spin. And I'll maybe jack this up a little bit so it doesn't take too long. And then let's watch it. Yeah. I sped this up, so it's pretty aggressive, but you can see that it kind of starts to tumble a little bit, and then the tumble gets worse, and then it starts to do the flat spin thing pretty quickly. Maybe I'll back off on this so it's less aggressive by a little bit. Let's see if I spin this a little slower and then give it less of a perturbation. But you get the idea. So this is basically the Explorer 1 phenomena. You start spinning like a hot dog, then with the tiniest perturbation, you get a little nutation, and then there's a bunch of damping. It starts sucking energy out of the satellite. Then it starts to wobble. The wobble gets bigger. Then you end up eventually in the flat spin. And the interesting thing, so if I plot a bunch of this stuff, we'll plot the energy and the momentum and all that stuff, and hopefully this thing doesn't die on me, and we'll do it next time anyway. This is the teaser. Okay, so this is kind of showing you, if I let this run longer, it'd be, yeah, this didn't kind of totally settle into the flat spin. Can speed it up and get there, but that'll be useful. Okay, so that's pretty much there. I could run a little longer. So that's pretty good. Okay, so that's clearly now. So we went from, spinning about the x-axis to crazy tumble to settle into spinning about the z-axis. And then this is all damping out. So this will asymptote out. Interestingly, okay, look at the energy. Here's that maximum energy state associated with the minor axis spin. And then we lose a bunch of energy because of damping. And then we settle into the flat spin in this minimum energy state. You can see it's kind of asymptotically. And then, but the interesting thing, right, is the total angular momentum of the system is still conserved, which it has to be, right? Because there's no external torque, it's all internal. So you're on the momentum sphere, but you still can have this kind of internal energy dissipation that leads to this phenomenon. With that, call it a day.